Section 1. A rainbow in a stone. Imagine a treasure chest overflowing with brilliant jewels, not just blue, but a dazzling array of colors. Picture a pile of sapphires shimmering under a bright light. Some are the deep, velvety blue of a twilight sky. Others are the soft, delicate pink of a blooming cherry blossom. Still more shine with the cheerful glow of a summer sun or the fresh vibrancy of new spring grass. One incredibly rare kind even captures the colors of a tropical sunset. It makes you wonder, why do these precious stones, all called sapphires, wear so many different and beautiful colors? What is the secret that allows one type of gem to paint with such a diverse and wonderful palette? This fascinating question leads us deep into the heart of the earth, into the world of mineral science and chemistry. The answer is not found in a single simple fact, but in a series of small, wonderful accidents of nature. Sapphires are a specific type of mineral known as corundum. Composed of aluminum and oxygen atoms arranged in a perfect crystal structure, in its purest state, corundum is actually completely colorless, as clear as a drop of pure water. The brilliant rainbow of hues we admire in sapphires is the result of tiny impurities, almost like a secret ingredient being added to a pristine recipe. These tiny additions are called trace elements, and they are the true artists behind the sapphire's colorful wardrobe. During the millions of years that sapphires spend forming under immense heat and pressure deep within the Earth's crust, minuscule amounts of other elements get trapped inside their growing crystal lattice. These foreign atoms are like tiny guests in the corundum's crystal home, and their presence changes how the stone absorbs and reflects light. This interaction with light is precisely what our eyes perceive as color. The type of trace element and its exact quantity dictates the final hue of the gem, from the palest yellow to the deepest purple. The world of sapphires is therefore a world of subtle chemistry and geological chance. Each colored stone tells a story of its unique formation. A few more atoms of one element over another can completely transform a crystal. The most famous and beloved sapphire color is, without a doubt, a rich and vibrant blue. This iconic hue is created by a magical partnership between two specific trace elements, iron and titanium. When atoms of both these metals find their way into the corundum crystal structure and sit near each other, they work together to absorb the yellow and red parts of the light spectrum, leaving the blue part of the spectrum to be transmitted back to our eyes, resulting in the beautiful blue color we associate with sapphires. It's a delicate dance of chemistry, a perfect collaboration treasured for centuries. The exact shade of blue can vary dramatically, from a light, airy sky blue to a deep, inky navy blue, and every shade in between. This variation is controlled by the concentration of the iron and titanium within the stone. Higher concentrations typically lead to a darker, more saturated blue. The precise way these elements are distributed throughout the crystal also plays a significant role. Even minute fluctuations during formation can create a unique, individual shade of blue. But the story of color doesn't end with blue. Another crucial trace element that can join the corundum party is chromium. When chromium replaces some aluminum atoms, it creates a completely different effect, producing shades of pink and red. A small amount of chromium results in a lovely pink sapphire, from pale bubblegum to intense magenta, romantic, feminine, and adored. Beyond the classic blues and pinks, the sapphire's palette extends into a surprising spectrum of other beautiful colors. Classic blue sapphires close up, classic pink sapphires close up, yellow sapphires, sunny tones from iron, green sapphires, earthy tones from iron, blue sapphire example, iron plus titanium. Yellow and green sapphires. Iron can act alone or sit in different configurations within the crystal. Small variations in the amount of iron and its specific atomic state can produce different hues. Pale, lemony yellow. Deep, golden canary color. Green sapphires can range from a light minty green to a rich forest green. often caused by a delicate balance of iron and sometimes trace amounts of titanium. The journey continues into the cooler tones of purple and violet, often created by a complex cocktail of several trace elements working in concert: iron, titanium, chromium. Some of the most intriguing stones are color-change sapphires, blue in daylight or blue under fluorescent light, but then shifting to a beautiful violet under incandescent light. One rare and exquisite variety is the Padparadscha, named for the lotus blossom. The journey of a sapphire to fine jewelry often includes one important step: heat treatment. This common, widely accepted practice enhances the stone's natural beauty. Jewelers and gemologists carefully heat sapphires in special furnaces to temperatures that can exceed 1,800 degrees Celsius. This process can dramatically improve a stone's color and clarity. Heating can dissolve silky inclusions, making the gem more transparent or deepen a pale blue to a richer, more vibrant hue. This isn't a trick to create color from nothing. It unlocks the potential the trace elements already hold. Intense heat can move trace elements within the crystal lattice, iron, titanium, reshuffling how the stone absorbs light and intensifying color. Sometimes elements that weren't contributing become active participants. Both natural color and treated color owe their beauty to the same traces. Treatment simply gives a final, respectful push. So, we return to the central mystery. Why can two sapphires, found right next to each other in the same mine, have completely different colors? Two neighboring rough sapphires in a mine. One might be a classic blue, while its neighbor is a vibrant pink or a sunny yellow. The solution isn't large-scale geology, it's microscopic chemistry. The answer is tiny, local, and wonderfully random. Inside one pocket of rock, the chemical environment can change over just a few centimeters. A tiny fluctuation in local chemistry is all it takes. Think of it like baking. One large batch of dough, and one small area gets more food coloring. As corundum crystals grow, one zone might have slightly more chromium, turning it pink. Another crystal a few millimeters away meets more iron and titanium, turning it blue. Heat can vary slightly, pressure can vary slightly, changing how trace elements are incorporated. Two neighbor stones can end up entirely different. Here's the simple payoff. Diversity comes from tiny, unpredictable, microscopic variations. The Earth is a chaotic, creative workshop. Each sapphire is a snapshot of one tiny spot at one moment in geological time. The array of colors is the result of this beautiful randomness. Sapphires wear their colors because of tiny elemental guests: iron, titanium, chromium. Trace elements plus subtle heat and pressure paint each crystal. Human treatments can further refine color, and inclusions can add special effects like shimmering stars. From blue to pink, remember the small story of chance and chemistry. A single atom can truly change a whole world of color.